Question 821 is titled, What is the equation? And the subtitle is Writing Equations Using Complex Roots. Okay, so today we're going to reverse your thinking to write the equation of a polynomial function given its roots. So far in this chapter, you have studied the attributes of polynomial functions, including how to write the equation of a function given its graph. Now you will reverse your thinking to write the equation of a polynomial function given its roots, even when the roots are not visible on the graph. So question 55 says, in previous lessons you have focused on real roots of polynomials, which are the x-intercepts of the graph. However, you have seen the roots of quadratic functions can be real or complex. Compare and contrast what happens with the graph and equations for three cases in parts A through C below. Okay, so for A, they want us to sketch the graph of the equation y equals x minus 2 squared minus 4, and they want us to say, what are the roots? Okay. So this one has two roots, one at 0 right here, and one at positive 4. If you FOIL out this x minus 2, combine it with the 4, and then factor it, you're going to have x equals 0, which gets you obviously the 0, and x minus 4, which gets you the positive 4. So your parabola is going to look like that, crosses the axis twice, so it has two real roots. For part B, now they want us to sketch the equation, quantity x minus 2 squared, and say, what are the roots? If you factor this, it's just x minus 2 and x minus 2. So repeat it, right? That's what we're going to call a double. Okay, so it has one real root, just happens twice, and it happens at positive 2. If you set each of those factors, x minus 2 equals 0, add 2 to both sides, you're going to get positive 2. And you'd get it twice. So that parabola is going to bounce off the x-axis right there at positive 2. Part C. Now we're going to change the equation just slightly to x minus 2 squared plus 3. If we subtract the 3 and then make the whole equation set equal to 0, if you do the quadratic formula on this, you're going to end up with what we call two complex roots. Complex roots end up having your imaginary numbers in there. And when you graph that one, that polynomial, it ends up being above the x-axis opening up, so it does not cross the x-axis. And its roots are going to be at 2 plus I rad 3 and 2 minus I rad 3. Same thing would happen if the vertex was down here and it opened down. Okay? So we're going to summarize this with part D. Describe the relationship between the graph of a parabola and the number and kinds of roots its equation has. So if the graph crosses the x-axis, it's going to have two real roots. If the graph just touches it, or what we call bounces off of it, it's going to have one real root. And if the graph is above, or like I said, down here and opens down, or below the x-axis, it's going to have two complex roots. All right, so at the top of page 15, you're going to see some review of some imaginary number problems. So they want us to simplify square roots, recall some facts about your imaginary numbers. So in prior math classes, if you had a negative under the radical, you would see, your teacher would tell you to write no real solution, right? But now that when you have a negative number under the radical, you're going to start to use your imaginary number, and the square root of -1 would be equal to I. So if you separate the square root of -11 to the square root of -1 times the square root of -11, you're going to have I square root of 11. For number 2, you separate it, square root of -9 to the square root of -1 times the square root of 9. You're going to have 3I. For number 3, you have the square root of -20. You're going to separate it to the square root of -1 times the square root of 4 times the square root of 5. The square root of -1 is going to give you the I. The square root of 4 is going to give you 2. And then the square root of 5 is some decimal, so leave it under that radical because it is not a perfect square. And then part D4, square root of -40. Separate it to the square root of -1 times the square root of 4 times the square root of 10. So the square root of -1 is your I, square root of 4 is 2, and the square root of 10 is not a perfect square, so leave it under that radical. Okay? Question number 56 says, determine the roots of each of the following quadratic functions by solving for x when y is equal to 0. So this is just putting what you know about imaginary numbers into practical use. Okay, so if we have an equation, we're going to set it equal to 0. Then we're going to isolate the part that's being squared by doing the inverse operation of adding 9, which is subtracting 9. And then the inverse operation of square rooting, or squaring, is to square root. So when you square root something that's being squared, you get what's inside. And then on the right, we have the square root of -9. So the square root of -9 is the -1, obviously comes out the I, and then the square root of 9 is 3. So for this particular problem, and then the last step would be to do the inverse operation of adding 5, which is subtracting 5. So we get 2 answers for this problem. One would be -5 plus 3I, and the other one would be -5 minus 3I. Okay? All right, let's do another one. Part B, first set it equal to 0. Then we're going to use more of like a completing the square type of problem. So if you move the plus 9 over to the other side, you would inverse it by subtracting 9. And then if you take half of -4, you get -2. So that's going to be your squared part on the right. And since you added 4 to this side, you have to add 4 to this side, which gives you -5. And then the inverse operation of squaring is square rooting, and I flipped sides to get my x, or my variable, on the left. So the square root of x minus 2 squared is just what's inside, which is the x minus 2. And then we take the square root of -5. So the -1 comes out to be the I, and then 5 is not a perfect square, so leave it under the radical. And then this 2, you're going to do the inverse operation to add it to the other side. So your 2 answers are 2 plus IRAD 5 and 2 minus IRAD 5. Okay? Yes? Oh, you're going to take half of -4, which is -2, and then you multiply it by itself. So -2 times -2 is 4. That's what we call completing the square. Okay, sounds like we need to do some lessons on completing the square. Okay. Yeah, you guys have learned completing the square, but it's probably in the recesses of your mind. So we will do some completing the square. Because you guys are all not sure on the completing the square. Completing the square is what you do right before you learn the quadratic formula. So the completing the square ends up being the quadratic formula. So once you learn the quadratic formula, some of you might forget completing the square. So you could essentially, instead of completing the square, you could use the quadratic formula on this problem. You could say A equals 1, B equals -4, and C equals 9, and then plug it into the quadratic formula, and you would get this same answer. Does that make sense? Yes? I can barely hear you. Say it just a little bit louder. Why do we add 4 and not what? Because -2 times -2 is +4. Okay. Yeah. So we're not doing at that point, we're not doing the inverse operation. We're adding something to one side. So if you add something to one side, you have to add it to the other. Okay. So clearly we'll do some completing the square problems, and I'll show you how that leads to the quadratic formula, because they're related. Okay. All right. Yes. Yeah, so I'm going to do a separate lesson on completing the square and the quadratic formula, but it might help to take out your headphones. All right, question number 57. What do you notice about the complex roots in problem 56? Describe any patterns you see. Discuss these patterns with your team, and write all of your observations. Both have complex, what we call imaginary roots. Okay. Up until this point, we've been seeing positive and negative numbers. Even some decimals are fine. But now we've got some imaginary roots. Okay? Flip over to the top of page 58. They gave us 4 of these problems, so I want you to skip 2 of them, but we're going to do B and D together. So in parts A through D below, look for patterns as you calculate the sum and product for each pair of complex numbers whose imaginary parts have opposite signs. So here are the 2 complex numbers. One is 3 minus 5i, and one is 3 plus 5i. So the first thing they want us to do is to find their sum. And when you find the sum or the difference, if they work the same, you're basically just going to combine like terms. Okay? So the whole numbers, the 3 and the 3, combine to get the 6. And then when you combine the negative 5i and the positive 5i, they're opposites, and they would cancel out, so you don't even write it. I mean, you could write plus 0i, but you don't need to. Okay? So you're just looking to add like terms. So the 3 and 3 are alike, the negative 5i and the positive 5i are like terms. They're opposites, and they cancel each other out. Okay? So clearly adding and subtracting, just find like terms. All right? For the product, we're going to take the 3 minus 5i and multiply it by the 3 plus 5i, which is essentially like a binomial times a binomial. And so we would FOIL. When you FOIL, you're going to multiply 3 times 3 to get 9. For the O is the outside. 3 times the 5i is positive or plus 15i. Then you do the inside, which is negative 5i times 3i, which is negative 15i. Notice these 2 are opposites of each other. And then for L, it's last. So you would do negative 5i times plus 5i, which would be negative 25i squared. I squared actually has a value. I squared is equal to -1. So when you multiply